Bao lâu nữa là chị mới khỏe? Bao tuổi rồi đó?
99 rồi em. Không có khái niệm có con, không có khái niệm khỏe đâu.
Không, lớn lớn dần. Chị đang chờ nó tới 6 tuổi coi nó có đỡ bớt không, chứ giờ nó 3 tuổi nó vẫn vậy.
Nó 6 tuổi bắt đầu lo nó vô cấp 2, nó học hết cấp 2 lo nó cấp 3.
Mà đỡ lo ăn lo ngủ.
Nhưng mà lo những cái khác còn mệt hơn.
Lo những cái khác. Tôi nói gặp tiền nữa. Chỉ nó học nữa.
Ví dụ lớn lên thì kiểu có giao du bạn bè,
có.
Kiểu nói chung là sẽ có những lo khác.
Đúng rồi. Kiểu gì cũng lo. Kiểu gì cũng lo đó. Đêm nằm trằn trọc.
Nói chung là chỉ là vấn đề lo ít hay lo nhiều vậy.
Đúng rồi.
Nếu mà nó cảm thông dịch cho mình thì mình có phước thôi. Đúng rồi. Máu đâu.
Là phước lắm rồi á.
Mèo nhà đêm cưng ghê. Em muốn chạy qua nhà đêm mà phải cắp con mèo á.
Anh có chục con mèo rồi, còn nhớ mèo người thì đó.
Không có chục con mèo không? Còn Tâm Tiên con mèo.
Nhưng mà
Tâm
chưa
Tiên
có
mèo
con.
Vinh Vinh kìa.
Dưới màu vàng nhưng mà chưa có con màu đỏ.
Chưa có một
Chưa có
cam,
con
con
màu
mèo
đỏ.
cam. Mẹ anh đi đẹp lắm rồi. Ủa là con mèo anh để anh đại diện không đi? Ủa gì? Đổi thành đại diện luôn rồi hả? Trời ơi, thiệt vậy luôn hả? Biết rồi, đúng rồi. Anh nhìn nó ngầu quá vậy?
Thì đã nói mà muốn chôn nó về ổng luôn.
Ủa, mèo bật nó cái anh đi.
Mèo BD.
Mèo BD mình sẽ mặc ngầu dưới đi.
BD
Nó quậu. Làm gì nó quậu với em? Ta là hoàng thượng đây. Ice cream.
Alright. So, look, this is industrial production of, well, that's the production, so that's the manufacturing
Dưới
side.
thì ngoài phải cầm cái ấm.
Of non-durable goods.
Cái gì tới cũng phải tới.
They're not durable. You just buy them and in a minute they
Sợ
go.
chị.
Yeah. And also frozen basically vegetables in the US. And that's nice. Yeah. We want to analyze it, forecast. So tell me, is it BTS station? So that's the first question you should always ask yourself when you want to do forecast. There's not a stationary series or not forecasting. Prices. Right? We don't know what is the price of apple tomorrow. We don't. So the best forecast for the price is what you know now. Because that's a, what is that? That's a market. Yeah. So prices are market. So based on the efficient market hypothesis, we know that the prices are market. Right? With the shocks, which are essentially small movements that are illegal returns, so the returns are not forecasted. So there is no zero correlation in the returns. So it's not something we know. That is getting right, so you cannot forecast the returns. If you could, then you would know, so tomorrow the returns are going up, so you would buy. Or forecast and then you see they are going down, you would sell. So you will not sell. And you don't know. Right? So if you knew, if I knew, I would use it, but then one of you will also understand. And then you will tell some other friend, and the friend tells the other one, and everybody start using it, so that our return just goes very fast. So as such, the returns are not forecasted. But they are sort of super. So at times one can get some episodes where you can say something about the movements, the very short time periods, and one can make money, but that's very short. So now I'm asking my question again. So I'm telling you, is it this ETS station?
We have to do the test. But if just look at the graph, then hard to say. It's, maybe there's a trend there, so I'm not quite sure. But this kind of like oscillation tend to say like it's hot. There's a chance that it may be mini stationary. But then if we want to be sure, then we have to do the test.
Well, that's true, right? We need to basically test. We actually said a lot of this stuff. Let's remember, remind ourselves, what are these? These are ice cream. And ice cream actually, well, that's a production.
There might be some seasonal factor.
That's true. So there is a season. People consume more ice in July. These are US data. Here there is time periods where you consume more ice. It's always
Summer.
Summer. Now it's summer. Right, so now we consume more ice. When it is winter, then not so much. Yeah? So there is also a season. It means that you have a time varying mean. Alright? And time varying mean by itself actually says that you can have weaker stationarity simply by the definition. Right? Because weaker stationarity requires mean to be constant, autocorrelation just to be a function of just the lag length. And here, by the very fact that you just said, and reminding ourselves, so this is ice cream, and that season is in summer there is more consumption, in winter less. So high mean, low mean. High mean, low mean. And this is what we see here. So I mean, we now want to look at the dates. I mean, these are generally June, July, these peaks. And these are December and January. These troughs. But apart from that, it looks like that in the beginning of the cycle, so the 70s, 80s, there was, apart from this oscillation, a constant mean. Right? Then there was some time where people started to say, ice cream. And they were consuming more, so it was produced more. For whatever reason, it dropped. And then it stayed for some time low, high, and then again it drops. And it's still higher on average, looks like, if I forget about that, compared to the previous one. So it looks like there is also a mean break. This is what I see in this type of series. It seems that there is a mean shift, sort of, there are some structural break that we have here and there in the mean, constant linear trend, and again the break in the trend, going up, coming down, more or less constant. So that actually speaks on its own that there is potentially some non-stationarity. Non-stationarity may not necessarily be that you have an AR1 with a coefficient of 1, which is an integrated of order 1. That's a classical unit group process, which is one way of having non-stationarity. Non-stationarity can be generated in different ways, by rates, right? By seasons, and so on and so forth. So it means that, so if I look at this, then there are, of course, variations. Well, you don't always, so there is a cycle, right? So we have to sort of take care of it, and then there is a mean shift. Right? So we have to take care of that too. Right? On the other hand, maybe you tell me, I don't care about 75 if I want to know something about 26. Who cares? Why should I care about what was my grandfather eating in the 70s if I want to buy for my child an ice cream? You know what I mean? So I mean that the data that we have here is not important. In 2005, there were sort of the crisis here. That's some short period again that we have had problems. Right? And so on and so forth. Probably the last data points are more important for forecasting compared to the back. Right? So though we see a lot of movements here, right? Maybe we sort of don't care about the past too much. Right? So now remember, when we start with an AR1 model, alright, so let me just write something. But let's say we have xt equals mu plus phi xt minus 1 plus the shock, epsilon. And let's say the processor starts at x0. That is sort of the beginning of everything. So what is x1? x1 is mu plus phi x0 plus epsilon 1. What is x2? Is mu plus phi x1, which is this, plus epsilon 1 plus epsilon 2. Which is what? Which is mu times 1 plus phi. So mu plus 1 plus phi plus phi squared x0 plus phi epsilon 1 plus epsilon 2. So I'm just recursively solving. Don't you? Then we'll go on. So what will be xt? So this is 2. And this is 2. So this is t. Alright, so that's this. What about that? So this
Minus
is phi to
1.
the power of 0 plus phi to the power of 1. But it was 2, so we don't go to 2, but we go to 1.
Minus 1.
That will be mu times 1 plus phi over 1 plus phi t minus 1. So that's sort of what we have. And what about this bit? So that's the last term. Epsilon t, epsilon t. And then this is one behind. Right, so this is phi epsilon t minus 1. And then it goes on and on. Right? T, phi, and epsilon 1. Very strong. What is the power? What is the power of this?
Minus 1.
1, which is very nice. That's 2 minus 1. This becomes t minus 1. Alright, so that's sort of the process. Now let's focus on this. This is my ground frame. Alright. And let's say phi is 0.7. And this is many periods back. Right? Say t is 50. So that's 0.7 to the power of 50. That's a small number. Times what he was consuming. So this just goes up. Right? So I don't care. Right? Means these ones, if I have a stationary series, will not be important. It will go off. They have an effect, but the effect is vanished. It goes off. Right? And this is something I'm sure we have done that before. It's just right there. You remember. Right? Good. So that's all right. But let's maybe start doing some, getting this data and starting looking at it using Python. All right. This is Fed. That's Fred. All right. So then we can get this data using Python, using the pandas data frame. Every now and we'll get it, and then start analyzing. So what I need here is this. That's the kicker. Alright. So all of the data that Fed has, they have this HTTP fred.series.org/series/the name. Okay, so that is what we need when we want to connect to this web page and get the Excel file or the CSV file, which is here. So we can download it here or essentially go as the beginning and the end. Alright, so that's what we have. That's monthly. These are monthly series. Alright. So let's start with warming up and starting to fetch the data and then doing our analysis. Let's import maths locally. Load SPFT, PDT.rc params, and set up configure.vbi119. So 600. Let's import pandas as PD. I'm happy with analyzing ice cream. Maybe you wanted that I analyze something else. auxiliary section, and then from the AR model, we import AutoRef. Well, I mean, there is also some model and something else which is called AR select order. Let's bring that to you. Okay? You remember how to select the order of AR models? We were using what?
Schwarz Kaiki.
Exactly. BIC, so Bayesian or the Schwarz information criteria, or the Akai key. So, well, in which I'm sure you know the theory, we can put them ourselves, so get the AIC, and then choose the order which makes AIC or BIC as small as possible, or we use this. Just doing the same. We let it. So that's sort of what we bring in first. And so that's the AutoRef, and then your looping. Let's go get the data. So the data, when we basically make a data frame from web dot, well, I mean, the previous one, actually, I used well, in the where did I do that? So that was the here, right? So in the previous one I used the data reader. Data reader is well, a powerful function, all right, but Fed by itself has in this pandas data frame has its own function. All right? So it's called get data from Fed. All right. So I will use that when you learn it too. Right? You can see they're the same. That's sort of. So you have get data. But I mean, there are different things. There is Enigma, there is Formal French, it connects to their web page, gets the data if you need it. Well, I mean, that is this is Fed, this, and so on and so forth. So Yahoo, which doesn't work anymore, and the rest is staying with Fred. So that's sort of what we have. Alright? And it says, okay, so give me the symbol. And what was the symbol? This. I'm just copy pasting this N, and then going here. Right, so that's the thread. And it says, okay, so when do you want to start? To sort of get the data. And I tell this, okay, whatever. Just go from the 75 January and end it. Well, so 2025 and 4 and 1. So that's April this year. Okay? And I wrap it in a data frame. Right? So that's one. Well, let's delete all those from the previous one. And then the plots we can delete too. So this one. So these are the variables. So that's the January 75 till April 94. Yeah? That is what we have. Well, I mean, this name we can change it. Maybe let's rename that. So that is data, or let's just rename it to, well, we can use a dictionary with this, we change it to us. And then axis is 1, right? So there is a column that we want to change. And then let's turn on the in place to be true. So it just changes it automatically. Right? So it's really nice. So pretty nice. Alright. Well, let's plot it. So log 6. Alright. ground. So what is autocorrelation at line 1, autocorrelation at line 2, without actually removing the seasons, without removing the breaks, just raw data, which you know is wrong. Theoretically is incorrect. Because, well, if you remember the Uwe Hasler's script, the autocorrelation that we have it will work only when you have weaker stationary. If you don't, then you can't use this. But I use it. Alright? I use it because oftentimes you don't know whether you have weaker stationary program. And then some very interesting features in this autocorrelogram will show up, that we can make up our mind and understand a little bit about the dynamics that we have. Let's then have a subplot of 2 by 1. Let's pick the fixed size as a 10 by 5. That's my favorite. And then the start plot. At axis 0, then we plot. Data.index, so that is on the x-axis. And then the data ice goes on the y-axis. So that is what we have. I don't need to make it more. Alright. Alright. Well, let's import. So here I will import stats modules. API as this. That's a very nice package. It will help us to do a lot of stuff. So let me just bring it into. And then here, well, I mean, there is SM actually has a function. Well, I mean, that is in the graphics. I think I told you in the previous section that we didn't do anything with it. So that's the time series setup. And then there is something which is called plot HCF. Alright. So what does it say? It says, what does it say? So it says plot the autocorrelation function. That's the autocorrelation. It calculates and it plots. That is what we want. So you remember the autocorrelations, how were we estimating them? So rho hat at lag 1 was summation of xt minus x bar times xt minus 1 lag 1 minus x bar divided by summation xt minus x bar. So that was the this is the lag j, and it would be lag j. So that is what this function uses. Right, so to do the calculation of the autocorrelation, and we give us here we say good. So give us autocorrelation function of ice. And then asks us where do you want to plot it, and we say put it in 2. And then asks for lags, let's say 30. Alpha is the 5%, well, that's 95% confidence band. There is a tightening. Well, so there are, you can correct the limits. And that's it, alright. So that's good. And then let's say we say PFT dot. You're right. So, what is going on? plotting them on top of each other. That was the point. Alright. You have typed this? You're so fast. Well, the data you have seen already, right? That is something that we saw on FED, on the web page. Right. So now there that we have the autocorrelation function. The shaded area is the consequence plan. Right, that's the 95% consequence plan. So what do you make out of this autocorrelation? That's true. This is on the face value it goes up and down. It is high, it is at 1. And then it comes down. When does it go smallest? Yeah, that's true. 18. Sort of 6. And then what is the difference between 18 and 6? Yeah, that's a year. Right. And then this sort of 28-ish.
Yeah.
30 or so. And so 18 plus 12 then is 30. So it looks like after a year then this cycle seems to repeat itself. What does it mean? So these ups and downs that you saw were indeed the starting point. Now I ask another question. When does it go up and when does it go down? When is it smaller? Then I found some sort of information. It looks like that every 12 months, which is a year, so sort of it goes up and then comes down. So something like this. So there is also another interesting thing to pay attention to. For example, when it goes up, then it looks like that this is like this. This is like that. Like roughly, these are similar. Alright? So it looks like that, and they have a difference of 12 months. These points that are big, they have a difference of. So it looks like that months of, that is July. July somehow seems to be related, more or less having the same autocorrelation, roughly with the last July, so the length. So 2 years ago is July, with 1 year ago July, and then 3 years ago July seem to have the same autocorrelation. So this is actually not because of, and then June is different. And August is different, a bit higher or lower. So something like this. So it looks like that the cycle that I see here, indeed, if I look at July's, then they are more or less the same months. They are strongly dissimilar, they are strongly autocorrelated. So then I see them to be more or less the same. And that's essentially because of the cycle. Right? So if you basically think of this as a sinus function, right, that repeats itself, so the movement in the autocorrelation is not because of the natural shocks or variations in the series, rather this is the mean function that is actually pushing this going up and down. So the mean, the season. The season is there, and it goes up and down, and this autocorrelation function actually is capturing the season, not the actual variation in the series. Okay. So if I want the natural variation, if I want to forecast this, then I need to know the season, because the season just repeats itself. And that's not very hard to get it. Alright? I can very easily just, fit the cycle, and then you are good to go. Alright? But then you can do it also differently. Alright? You don't need to go into explicitly talking about the series. Now remember that we said Novembers seem to be similar because people don't consume much. Decembers seem to be similar because that's sort of in the heart of the winter. So is January. But then July is different. It doesn't matter if it is 2025 or 24, it's always hot. Right? So it looks like that These mean shifts we can capture using a season, a dummy. So sort of you say that the mean of July in all of the years is more or less the same. You capture that not with this actual season, but rather with dummies, months. So you can do that. And then you always know, right, so the coefficients you will guess. So here we have 12 dummies for each month. And then we capture. Right? So then we'll actually capture the season. See, so look, I mean, if I didn't know that these are eyes, then I would have had a hard time understanding. I had to really think hard. What should I do? But because we know that this is eyes, right? So that's a very valuable information. So whenever you do forecasting, you have to always like make yourself like think, what do I have here? Then what am I analyzing? So exactly. You have to really think. Right? So once you start thinking and understanding the series, then you come up with ideas that you can embed in your models, in your econometric models. Remember, econometric is economics and metrics. Economics is the logical side, and metrics is all the calculation and multiplication and 1 plus 2 is 3. So that's the numbers. We basically, when we understand that these are series which are what, then it becomes easier to analyze. That was a bit of reminder that you have to always think of these series. But this was sort of, I mean, a fun series to analyze. And we could put this specific. Well, yes. Sure, exactly. So that's the dummy variable track. Right? So we need to take care of this carefully. So you can have that and the constant. You can have just one constant and then keep January out. Or keep the constant out and then have all of the dummies. So you don't have the dummy variable track. Okay. So let's go on and let's start analyzing. Analyzing this series. So here I want to have a dependent variable. Alright, so let's put it there. Dependent variable for y, and we want to analyze. I don't want to carry with me this data eyes all the time. Alright. But now here, because we are doing forecasting, then we have to indeed set the frequency of the data explicitly. I have to say that hey, this data that we have are, because now we will go and then forecast. This forecasting, so we understand that these data are time series. So that's the time you make it instead, and you set time. Right? Basically, you do that. Right? Here you do it too. And if you don't do it, then I think there is a function that infers the series, the frequency from the dates. That is possible. But let's do that explicitly here. And then we say, all right, so here we have a frequency data. So we set them as some data which frequently repeat themselves as ms. So ms is indeed the monthly frequency. So if we control G this, then there are different options of this. 30 seconds. And so on and so forth. So you can essentially check whether the frequencies exist by simply looking at what the background. The shortcut is Ctrl G in Windows. Right. So now that we are here, then we can go on. And let's see what is the sample size. And then maybe the length of the index. Right, so that is what we have. That's the sample size. And let's start doing some forecasts. Alright, let's take it easy. So that's as Freck actually sets the frequency to monthly. Right. But let's, I gave you a lot of discussion that this is monthly, we have to take care of the dummies and But let's say we are lazy econometricians and then we say, oh, what the heck, let's just use AR3. Alright? Maybe it will be good. Alright, we are first lazy, but later we will do it better. Okay? So let's actually have a AR model. Let's go to model AR3, which we basically do as simple. And here we have actually the auto rec. Later we will do a bit more. So here the dependent variable is for depth. Alright. And then we have to talk about the lags. Let's say it's 3 as I just said. And then we do a fish. That's all right. So that is the testimony uses. So that's the depth, that's the time, and that is the model with the phase. Right? Maybe before we go on with our forecasting, right? So model, we estimate that, but I will actually print the model under AR3.sum. Just want to know what is in there. So that's the model. Variable is for ice. That's an AR3. Number of observations 604. This is the sample size. And that's the constant. And these are the phi1, phi2, phi3. So all of the AR coefficients. Right? And then here we get the modulus of the roots of the lag polynomial. What I said made sense? My last sentence. Do you understand what is this? That's right. So these are the roots of the lag polynomial. And this is the length of it. Do you need them to be larger than one or smaller? No, these are the roots. Okay. So let me remind you of this.
There's a different way of having the characteristic.
That's right. That's right. Now let's look at this model, alright? This one that we have used with the input, right? So if I want to have weaker stationarity, then I need absolute value of phi to be smaller than the right? That is what we need. Okay? So the root, that's not a root, but that's the phi1. Phi1 should be small, so you have weaker stationarity. But let's write the lag polynomial. Lag polynomial is 1 minus phi L. And that's the lag polynomial. And then from that, then we can write the characteristic polynomial, and that we replace L with Z. So here, let's say we have phi of Z. It is 1 minus phi Z. What is the root of this? Root of it. Say we set this equal to 0 and then solve for Z. So if I want absolute value of phi to be smaller than 1, then absolute value of Z will be
Actually,
larger. Alright, so this is the absolute value of Z. So that's the modulus, that's the length. And these are the length of the roots. Here we have a polynomial of order 3, so it has 3 roots. The roots are imaginary, so they are non-real. They have the real part and imaginary part, and that's the length of it. So this to the power of 2 plus this to the power of 2 squared root. And then all of those roots are bigger than 1. And that is what we need for weaker stationary, or at least the stability. Let's not call it the stationarity, but stability. So we need these to be big, bigger than. These are not the fees, but rather the roots. The length of the root. So that's good. So whenever you have an ARMA model, you just look at those and then see they are bigger than 1. If they are, then you can go for it. As I said, so you are lazy, you don't do much. You don't care about the mean shifts or the monthly effects. Alright? Well, so far so. So if I'm here, then maybe let's do a forecast with this. Alright? And the forecasting is actually very simple. Let's generate a figure. I call it figure of AR3. Alright? And that will be, so that is model underline AR3, because that's a dynamic model. Then you can easily plot the predictions. So here plot underline. What does it offer? Plot predict. Well, let's say we go 20 months back and 12 months ahead. Let's see if it works. Why doesn't actually give me anything? Hurrah! It is working.
Đẹp quá.
Alright, so these are the forecasts. So let me make it a little bit more readable for you before we go on. Look, I want to add the actual data to this graph. The actual data I want to add to this graph so you see, look, this is the end of the sample with the gray one, the gray part, so that is a 95% confidence. It automatically calculates. I don't need to tell you this here. Calculating it does. But before actually this gray line actually sort of starts, then we have the inside. So that's 24 months. So because here I said T minus 24, so that is an insider, so that's a simple prediction, but 12 months ahead, so that is a forecast. And that's pathetic as a forecast. Because it somehow doesn't get any peaks. It simply keeps midline. It's good enough. Sort of is not really good. Okay? So because we didn't care about the cycle, and maybe AR3 is small. Maybe we need a longer line. Actually, we need a longer. Why? Because we have the structural breaks. Right? So whenever you have the structural breaks in the beams, then AIC models generally choose a very big line. Because a structural break is mistaken as a unit root for a long series. If you have a unit root, then you have infinite paths, essentially. Everything actually matters. And as such, then you would choose a long further regression. We will come to this. Let's add a little bit further. But if I want to add something to this graph, then I need to get the axis. Alright, so I need the axis back. And when I say, well, hello PNT, so that's the matplotlib, get the current axis and give it back to me. Alright, so that's GCA. It also works in MATLAB. So we will get the axis back. Now we can do whatever we want. And then let's do the following. So here we say on this axis, then plot the data.index on the x-axis and data ice on the other axis. Right? And then give it the label, you don't need the label, you understand what it is. Maybe we also do let's do the following. Let's set the bounds. So we don't actually need all of the data, right? Because the data, these are very few. That's 3 years. But then the sample size will go to 75. That will be, the stretch will be very large. You'll not be able to see what happens in the in-sample part. So we set the x bounds here of this axis with a date. Right? So from some date to some other date. But let's maybe import the date time. As dt. Is it date time? Date,
Date.
not date time. That's the date time, which we break it as date. Let's activate it, run it here, and then here we go and say, alright, so dt help us to put together some dates, right? And then here is the date, and then we say, well, okay, go to 2025, go to 3 years back, becomes 25 minus 3 is what? 22. 2022, say this month, right? So that's the beginning, and then dt also give us a date. That was 2025 with 4 and 1. Alright, so that's the bound. That should be good. Let me just see if it works. Well, actually, we have to go to 26.
Six.
Let's go to
Oh,
6.
yeah.
And then make this 6. Alright, so because the end just it cuts off. Alright. So now it's a little better, right? So you see the orange line, I didn't add a label. The orange line is the true values. You have the true industrial production. The blue line is the forecast, but that's in sample. And that's, in sample we pretty much get what is going on. Right? But out of sample, no. So that is not actually a good one by simply looking at the forecast. It doesn't get any cycles, right? And some are flat. Simply gives me a mean. Right? So that's what it does. And we need to capture the cycle. But maybe before I go on with sort of doing further analysis, I boil it, I look at it, and I see, in sample is good, out of sample no. We can look at some further diagnostics of this basically series, sort of the estimated number. Look at its impacts. Look at the residuals. Those residuals are what are left, as I'll explain. So that is something which we need to look at carefully. Let's generate a fig of diagnostics for the AR3 model. And that will be what was the model? What was the model under now AR3? And then here we say plot underlying diagnostics. And then here let me add a max of 24. We will see why. And here we make it a bit smaller or somehow so you can see. Look here, we have a figure. I I quoted the diagnostics for this AR3 model, and that's what we are estimating. And in here, and that's a wrapper, we use a lot of things, not only the parameters, the standard errors, and the modulus, and so on and so forth, but it uses the residuals, the fitted values, and a lot of other things. And then this plot diagnostics actually gets some excerpt, some summary of the results of that model, and then shows us. Alright, so I want that you look at it, and I want to discuss what these guys are, what do they think. Alright, so that's the graph. Well, I mean, we can make these dates better, we can turn them, and so on and so forth, but this is beautification and just cosmetics and leave out. We take time. After we'll get all of the tickers and turn them. It's something. I can, at night I will program in an hour before I post this. But let me just focus on the main basic results. These are the residuals. The first one. Okay? So, you like them? I don't. Because residuals should not have any visible pattern. They have to be totally random. They are not. So sort of, you remember there was a meme, I said we have to take care of it, we didn't. There is cycles, we didn't take care of it. And so on and so forth. So the most visible part in this basic graph is the peak which we more or less have in the middle. Remember, the series here had a peak. There, gravity is small, so there is a peak. So it was going up, and then coming down. And that's the same in the residuals. In the beginning, the mean was fixed, slightly going up, and then again going up and down. So these movements are in the residuals. We didn't take care of them. We didn't. They are there. Because we didn't remove them. So why should they go off? They don't. They stay. So let's look at this graph, which is not so important if you understand how it is generated. Because we discussed it the last 2 days. The green, the smooth curve, is the standard normal curve. The orange one is a kernel density estimator, which we know how to do with ourselves. So, and then if I look at this, then sort of the residuals we take and then calculate the kernel density estimator, and you see they are not normal, so who cares? OLS doesn't care about this standard normal. If they are normal, if the residuals are normal, then we will be closer to the Gauss-Markov theorem. Gauss-Markov theorem, what does it say? It says if you have the residuals of the error tends to be normally distributed, the model is linear, then you have the most efficient estimate. That's the best linear unbiased system. Best in the sense that it has the smallest variance. But if it is not normal, then what can we do with the non-normality? They are just not normal. And here they are not. I don't care about that. So it means that if my estimators are not the most efficient, but that is what I can't do that. That's an irrelevant graph from my point of view. But the nice thing about this is that it reminds you of the last 2 days where we were doing the kernel density estimate. That is, we know how to generate that graph. That's such a SNS. So let's see what. You sort of get the kernel, the sample, or the bandwidth is n to the power of -1/5 times some values, and that's it. So let's look at this. So this is the autocorrelogram of the residuals. So the autocorrelogram of the data themselves before the AR1, the raw data. Raw data had such an autocorrelogram. So a lot of autocorrelations because of the cycle, because of whatever reason that we discussed previously. Right? So if I look at the graph that I have now generated, right? So we had an AR3. And AR3 conditions on last month, or today on last month, and then the other two, three. You have a lag of three. So AR1 is actually capturing a lot of variation. So it captures the cycle, but not totally. Right? So here, this is again 12, and that is 24. So, well, I mean, these two peaks are standing out to be killed. Yeah. You should shoot them. Yeah. So we need a stronger mode, a better mode. Maybe we should capture the time varying mean somehow. But I mean, this AR3 actually does a good job in capturing the cycles or the variation. To some extent, not totally, but does something. Alright. But this graph is well, that's a QQ plot, right? So if these dots, the blue ones, if they were aligning on the red one, we would have said that we have a standard law. Right? So if I look at this, then there are some problems. They're not few, there are so many. And then there are also a lot of other problems. And they are in the tables. And these are because of the peak that we have up there. Right? So big positive values. And they show up there themselves. So they go deviate from the red one. Right? So this is not probably, so now this actually to me means maybe the data are really normal after you take care of the cycle properly. Maybe these guys that we have there are because of the mean shift, which we didn't take care of, or the cycle, whatever. But in any case, they are there. So the usage of this QQ plot is to make you aware of the potential very many outliers that are generated because you didn't take care of the mean shift. You didn't. That is there. Look at them. You look at those in the middle, where they very much go above 2. Right? So they are very big ones, the outliers, and they show themselves here, and then very big, and there are not so many big negative ones, but there are some. Right? And then they show up themselves there. But not too many. That's sort of not so dense. But there is dense on the other side. Alright. So that's the story. That's how you would approach understanding whether your model is good or not. Right? So whenever you do forecasting, look at these graphs. Think of them. Make sense of this. Look at the residuals. Because if the residuals are not random, if they have a pattern, it means you didn't do a good job. Your forecasting will make you fire it. You will lose your job. Or your money. Right? So if you're working for yourself, so you look at those. Well, let's do a little better stuff. So that was an AR3 model. Let's do an AR12. Right? So if we have 12 models, then why not do an AR12? Right? So maybe it will be a better one. Right? Let us redo this. So I will just take all from here and then paste it down. So here we do an AR12. And then we call this 12. The lines become 12. We look at the summary. Let's do it 12. And also 12. Here 12. That's also 12. Is there anything else we should change? It makes sense to do it in a loop and then better. Let's enjoy. Let's put this step by step. So first we need to fit with 12 lines. Oh, I wait. I will wait so that you change this 3 to 12. let's look at the forecast of this model. Oh, that is a lot better. So it sort of, it doesn't give me a line, right? But it gives me
Curve.
somehow it captures the side. So that's sort of, well, that's actually very nice. I mean, about the AR models. Look, we haven't done anything with the side. But still, this model is capable of capturing the side. So that's interesting. One can do better. I mean, there are seasonal ortho models, of course, right? So we can do static models. So seasonal autoregressive integrated moving average models. We can use them. But I mean, with this simple one, it seems that we are capturing a lot more than before. Well, let's look at the diagnostic state. Right? So just to see how good this model is. All right. And let's see. Oh, all right. So that is the stuff that we have now. Well, I mean, that is sort of still not. I'm not still happy with the residuals. They became a bit better. Okay. So, but it's still these. Well, I mean, these guys are there. That is the ones which we have, these peak ones, going well above 2. These are those. These are above there, maybe. So they went off. These autocorrelations, they're still there. They still have some below. You have to sort of shoot them further. So they go. They're still there. They became smaller. We need the sharper sword. But we're using less. So less pronounced. It's a bit better. Well, okay. But we are just fumbling around, trying 3 and then 2 and then 5. Maybe we do a little better. So, sorry, this is such a funny stuff. You can do, maybe before I go on with, with choosing the ligand, I simply tell you how to take care of the, so let's do another model, so that's AR12 with seasons, or with periods. Right? So here I want to take care of the niches. July is not July, January is not January. Alright. So period of 12. We can have period of 2. And we say the first half of the year always are the same. So January to June is the same as this is July to December. And then we have January to June. Sorry, I just mixed over the months. So 1 to 6 is the same like 1 to 6 next year. So that will be a period of 2 or a period of 12. So we can do whatever we want. So let's do this auto regression. So here we just then again copy paste the whole thing. These lines, bring it here. And then here I will add an underline head. So this means that we are taking care of it here. So to do that, then we simply say so there they are here. Wait, so then we see them in front. There is a season, and it is false. You turn it off. Come on, take care of this season. And then there is a period, which is not. We will set it to 12. So, we do that. Here we have a season. We say, well, we have a season. And then, true. And then we have a period becomes pale. This is pale. So the only thing that I did was change this. Alright. So just wait so that you type and make the changes. Yeah, you ready? Alright. Then let's run it. And let's look at the results first. The summary of the estimations. Look here, so Uri was worried about the dummy variable trap, and it actually does it. So this is season 2 in 12. There is no one, but there is a concept. So, that's okay. I could actually go and interpret these values when I read one time. So these are the means. With respect to relative means, with respect to this. You know what dummy value is. Right? So then we make this is the base mean. And then here you have the additional values with respect to what our seasonal so what the important part for us is to look at, well, look, I mean, these means are all significant, so which is not a surprise. We knew that Januaries are different from March. March is different from June. They are different. So these p-values for all of the seasonal quantities are zero, also relative to the quantities. And then so those coefficients are also, many of them are relevant, some not. And then in the end, then we also have another batch of important ones. Right? It looks like that this 12 may be okay. Indeed, we can choose it using ARC. Right? So we do it like that. And then these modulus stuff, they all be. So now then let's do the next step. Alright. And that is the new one, right? So let's look at this and that. So this is AR12 without seasons. This is AR12 with seasons. Which is better? Right, so this and this. Or okay. What is the difference between them? This one and that. That's right. One. That's true. Very good. This was here. Basically took care of the mean shifts. So we reduced the ambiguity. Previously we did. And these sort of unattended mean shifts were going in the residuals. And the residuals are very important to calculate the confidence bands. Confidence bands are based on the residuals. Right? So the sum of theirs are coming from that. And those guys are viable compared to this. So that is a better one. So it captures this item, okay, a little bit better compared to the previous one. So it sort of moves from there's a sharp peak, keeps, captures. And that's July. Right, that's July. Right, so that's you see, that's 7. That's a July. That's the peak where you have the most consumption. that is something we get. There we also more or less get it, but sort of more flat. This is a little bit better.
We can predict the sign as well. That the sun highlight.
Yeah.
So the model like this like the trial for regular impedance is like one light, two lights behind.
Yeah.
With the limits.
Sure, it's good. It's a good one. So you are happy with this?
Yeah.
Me too. So let's look at the diagnosis and let's see what happened to these ones. Maybe they are dead or not. Oh, they became smaller, but they are not dead.
Still.
Okay. So I think you did a lot of this stuff, so you tried very hard. Alright, so we have the seasons, we have more lags, and so on and so forth. Maybe we add more lags. So instead of 12, we use 24. Yes, so maybe more. Well, we have 600 data points, so that's okay. So we can indeed estimate more perhaps. But then if we had few observations, and we couldn't add many more lags. So if I had say 150 observations, then I would have been a little bit unsecure if I was estimating an AR 20. 100 observations, and estimate 20 plus 1 parameters, it would be too much. So then, so in this type of situations, then say data science would be helpful. So one can shrink the dimension. Well, if you sort of, this is actually could be sort of kick out some of the lags. Maybe lag 1, 2, 3 are important, but not 5, 6, 7. Right? And again, say 8, 9, 10 are important, but not 11 and 12. So maybe we don't need all of them. A few of them would be maybe enough. So there are a structured way of understanding which of these is important. And that becomes a little bit, goes a little bit away from the classical regression analysis, and that becomes something else. Right? So there are ways of doing it. Okay? Right, so these peaks became smaller. The residuals are a bit better. So this patch was going up, now it doesn't. This side is better. So the orange and the blue also fall more on each other. So we are doing better and better. We have 5 minutes.
Yeah. 2 minutes.
Sorry?
2 minutes. Yeah.
Let's stop. I just wanted to choose the lag length using AR select, because that was a function that worked what we need with the ARC that I do tomorrow. Thank you very much.
Thank you very much.